Hey everyone! In this video, we're going to introduce formally the transpose of a generic matrix A. As you can see here, the transpose is denoted by A to the T, so to speak. There is no exponentiation, it's just the notation. And its definition is really very simple. The rows of A are the columns of A transpose, or the columns of A are the rows of A transpose. It can be seen in both ways. I'll highlight one here just so we can see clearly that the first row of A becomes the first column of A transpose, and the second row of A becomes the second column of A transpose. The definition is very simple, very easy, but now let's look at some of the properties that brings. The first property over here says that you could first add two matrices and then transpose, or you could transpose two matrices and then add, and the equality says that the results will be the same. And this makes sense because addition of two matrices is done term by term. So you could say the rows of A add with the corresponding rows of B, and then when you transpose them, those rows become columns. Well, here, say the first row of A is going to be the first column of A transpose, the first row of B is going to be the first column of B transpose. So if you're adding the first two rows in A plus B, here you're adding the first two columns. So this is really very simple and very easy. The product, however, is not as trivial to see that this is really true. So just like with inverses, we can transpose the product of two matrices, and in the transpose, the order of the matrices changes. So if we had A times B transpose, here we're going to have B transpose times A transpose. Now, let's see why this would be true. To begin to understand why, so here we're trying to understand why AB transpose, so the transpose of the product, is the product of transposes but in reverse order. You could take two matrices A and B that will have that will not be squared. Say A is of size m by n and B is of size n by k, and then you will see that sort of just the dimensions in order for the product to work in both cases makes sense, but that would not be a proof. So we're going to start to tackle this. We're going to start with something simpler. We're going to take the case where B is just one vector, for example, the vector x. Let's look at A times x for this A and some vector x with three components. I'm going to carry out this multiplication by expressing AX as a linear combination of the columns of A. So I will have x1 times the first column of A, 1, 0, plus x2 times the second column of A, which is 2, 0, plus x3, which is times 3, 4, which is the third column of A. Now, if I were to find, if I were to look at the transpose of A times x, I know that, so obviously that is the transpose of the sum that I have here on the right? But by that first formula, we know that I could just transpose each component and things would make sense. Here, the x1, x2, x3 are just numbers, so there is nothing to transpose. So if I want to transpose AX, I could just transpose, I would be transposing these columns, which equals, maybe I'll stick with the pink, x1 times a row vector, if you wish, plus x2 times a row vector 2, 0, plus x3 times a row vector 3, 4, because that is what that T is doing. It's converting columns into rows and rows into columns. All right, so I have an expression for AX transposed. Now let me look at X transpose A transpose. I'm going to write this X. So X transpose converts X into a row vector with components x1, x2, x3. And A transpose now will have columns 1, 2, 3, 0, 0, 4. Now, if you remember when we talked about multiplication of matrices, we have 4 ways of multiplying matrices. The first way that we used to compute A times X was just expressing the product as a linear combination of the columns of A. Whereas now I would like to use the column times row approach to multiply that product. So to compute the product. So I will have x1 times the first row. So we can do, let me write here, columns times rows. And it really has to be the corresponding columns, right? The first column of X transpose times the first row of A transpose, and then the second and the third and so on. Plus x2, 2, 0, plus x3, 3, 4. And what do you see? Well, this is exactly the expression that we have in pink, which is AX transpose. You see, AX is an expression, is a linear combination of the columns of A. Whereas X transpose A transpose, if you look over here, is a linear combination of the rows of A transpose. But the rows of A transpose are the columns of A. So indeed, X transpose A transpose equals AX transpose. Now, how can I use this intermediate step to show that AB transpose equals B transpose A transpose? Well, let me look at what is A times B. I can express B through its columns. So let me write here some matrix with first column B1, second column B2, and so on up to BK, whatever, assuming B has K columns. Well, this gives us the matrix with first column AB1. Remember, a matrix times a column is equal to a column. So AB1 is a column. AB2 is another column, all the way to ABK. Now, when I transpose this expression, AB transpose, I'm transposing this last matrix, which forces me to write the columns as rows, because that is the definition of a transpose. So I need to write this column, AB1, as a row, which is to say I should write AB1 transposed, and I'll write it as a row here. And then I have AB2 transposed all the way to ABK transposed. But that is the same by what we showed in just the line above. That's the same as B1 transpose A transpose, B2 transpose A transpose, all the way to BK transpose A transpose. But that is equal to B transpose A transpose, where I'm carrying that multiplication by using the rows of A transpose. So the 4 ways of carrying out the product A times B is incredibly useful here to show this proof. So now what we have done is we have proven this second step here, we have proven that the product actually holds. And we will use that product to prove that the statement about the inverse. So what is the statement about the inverse? It says that the transpose of A inverse is the inverse of A transpose. And now using the statement about the product is actually, this last step is very easy to show. So we are trying to show that the transpose of A inverse is the inverse of A transpose. How can you show this? Well, we start with the fact that, of course, this is the case when A is invertible. If A is not invertible or A is not a square matrix, this doesn't even make sense. So assuming that A is an invertible matrix, what we know is that A times A inverse equals the identity matrix. Now, recall that the identity matrix is a diagonal matrix with ones along the diagonal. I'm not specifying here a size of A, let's say, let's say it's n by n. And there are zeros above and below the diagonal. So as you can see, if you try to find I transpose, well, I transpose is equal to I. So the matrix I is equal to its transpose. Okay, so if we have this equation that A times A inverse is the identity, what I could do is I could apply transposition to both sides of the equality. So if A times A inverse equals the identity, then A inverse transpose equals the identity transpose, which is still the identity. Now, by what we showed just a minute ago, what we have is A inverse transpose times A transpose. Remember, when we take the transpose, we reverse the order, is equal to the identity. Now, from the fact that inverses are unique, it turns out that the inverse of A transpose is A inverse transpose. So the inverse of the transpose of A must be this other part, A inverse transpose. So we have shown that these three properties, so the sum was very intuitive, the product and the inverse all hold. Now, note that from the last property, we see that if A is invertible, then so is A transpose. And if A transpose is invertible, so is A. So, in other words, we can write here A transpose is invertible if and only if, so this double F means if and only if A is invertible. And again, this if and only if says that if A transpose is invertible, so is A. And if A is invertible, then so is A transpose. One final comment before I close this video. With this new notation of transposition, we can actually express the inner product of two vectors. So let me write here, the inner product, or the dot product if you wish, of two vectors x and y. So remember, we have we always think of our vectors as column vectors. So x has components x1 all the way to xn. Y has components y1 all the way to yn. And in fact, we can think of the dot product x dot y as the product of the matrices, the first one having a row with components x1 through xn, and the second one having components y1 through yn. Well, now the first vector is just x transpose. So I can write here that x dot y is simply x transpose y. And this is very powerful. And you can see that you can also write the dot product because I don't know if I've mentioned this, but it is obvious. X dot y is the same as y dot x. So you do have commutative property of the dot product. And now you can write y dot x by what we just wrote as y transpose x. So we see here that x transpose y is the same as y transpose x for column vectors x and y. And now what is interesting is that this transpose is in between x and y, and that is the reason for this inner product labeling, because that t is in between x and y. We also have something that's called the outer product. Of two column vectors x and y, and that is defined as x times y transpose. So you see the t is outside, and that's why we call it an outer product. And if I were to write this, just so you guys can see it, I have x is a column vector, whereas y is a row vector now. Y transpose, sorry, is a row vector. And what this does is it gives us a matrix. This matrix is going to be, well, let me just write, this is y transpose. So the matrix is going to be x1 times y transpose. Remember, x1 is just a number. So what we get is a multiple of the vector y transpose, or the vector y written as a row. Then we have x2 times y transpose all the way to xn times y transpose. And this matrix is a matrix of rank 1. And what that means is that it has only one pivot. Now, of course, here we don't see the pivot, but if we were to carry out elimination, we would only have one pivot. Even though we're not seeing, and of course, this rank 1 requires that the vector y is non-zero. If it is 0, then this is not a very interesting discussion. So assume that x and y have at least one component which is not 0, both of them. Now, why can we conclude that this is a rank 1 matrix, that this matrix that we get, this, oops, my bad. This was x, y transpose. So the question was, why is this x times y transpose a rank 1 matrix? And if you look at what we got in the end, well, you see here, this vector is a multiple of y transpose. This vector is also a multiple, which means that the space that those two describe is just the line that passes through the vector y. Well, this one over here is also a multiple of y. So you see all of these rows are actually multiples of y transpose, which means that after we carry out elimination, only the first row will survive and all the other ones will be 0, hence the rank 1 matrix. All right, that's enough for this video.